Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
All right.
We are here again.
Hello, everybody.
It's 2 weeks in a row. We're on a streak.
Yes.
It's a hot streak.
Yeah, that's right.
It's like sports ball's about to start again. Just so you're aware. I know this is not your favorite thing. It's my favorite thing.
But is that how you like? It's like the calendar is based on.
It is
relative
really
different sports ball events.
So in America, basically all summer is the worst sports ball time because the only sport that's occurring is baseball, and baseball is kind of boring, right? Like it's fun to go to a game if you live near a major league, baseball park or whatever. Going to the games in person is kind of fun. It's actually kind of fun to go see teams play. It's got this sort of picnic atmosphere.
Yeah.
It's pretty low key. It's casual. You're not, even if it's your favorite team, it's pretty nice. It's just chill. You know what I mean? You're outside most of the time. It's kind of like, yeah, get a hot dog and 53 beers. And then, you shout at the umpires when they get a call wrong. It's great, but it on TV, it's just boring.
You just think it's boring.
It's pretty boring. I used to love it. I used to be a huge baseball fan, and I'm just like, now it's mostly I like hockey, I like football, American football, and basketball a little bit. I like it less. I like hockey and football, and it's just.
Wait, you like basketball less now?
That's correct.
Really? That seems
correct.
like a new.
Basketball is my favorite sport to play, and my third favorite to watch.
Okay, all right.
Yeah.
The top three is pretty good. Top three is
out of
not
4,
bad.
so no.
Oh, out of 4.
That's bottom 25th percentile. It's like no.
Well, yeah. Well, then what's your fourth? Is baseball?
Yeah.
My favorite. So baseball and basketball.
Yeah, the order goes hockey, football, basketball, baseball.
Oh, okay.
Yeah, I definitely like hockey. It's my favorite, and we're still like a month away from NHL games, which is just sad. Why isn't it all year round? I know that these players probably deserve rest because it's tiring and it's a hard game, but I don't care. Play games.
It's your job.
Play more sports for my entertainment. I have a long summer with nothing to watch, and they're not thinking about my feelings. That's the problem,
That's
but it's all about to come to an end because football is coming back. And this is all related to what I said originally, is that we have now gone 2 weeks in a row of this live stream. And so we're on an epic sports ball streak. It's like a winning streak.
A sports ball streak.
That's right. 2 wins in a row.
Casting streak.
That's correct. It's a live stream streak of epic proportions.
Yeah.
And so there, just next week will be 3 in a row, and then then our streak will end.
And then the streak will end.
That's right. But it's still an impressive streak.
Yeah. Well, I mean, we used to have this like every single weekend. It was not a problem. But then, travel happened. Workshops happened. Workshops are now done. So if you've attended or are interested in attending workshops where we host with a professor at a local university, we tend to do a lot of electrochemistry workshops to actually put some of the skills into place. And so also, even if you may be a student, trying to learn some electrochemistry, we actually do a lot of the help for professors. So if a professor is interested but doesn't have all the tools, we actually have a lot of the resources, potentiostats and electrochemical cells, electrodes, a lot of the accessories that you need to make a workshop happen, as well as clearly a lot of pedagogical content that we put out. So that's done. That won't happen until next year. But in the meantime, before we actually start, I would like to promote, for those who are watching, next week, I will start a voltammetry webinar series. So
it's this one right here while we're
at it. While we're at it.
So this, you can see on our website here,
Mhm.
when you come to our website, there's a webinars tab at the top. So you click on that and you'll see all of our upcoming webinars, which are all right here. And that's where you can find the voltammetry series.
Yes. Yeah. So it'll start next week, Thursday, 8 a.m. EST, but also 4 p.m. EST, just for people of different time and in different time zones. And then, of course, if you can't make either of those, this will be on YouTube. So even if you're watching on LinkedIn or something like that, you'll still be able to access the videos, or if you're sick or something like that. These things happen, so there is still time to watch it and catch up, so you can make it to other future webinar episodes.
That's correct.
Yeah. So
while we are here, if there are questions, go ahead and type them into the chat anytime. There was one question on the YouTube channel a little bit ago. I assume sometime this morning, I think, was sort of typed in here by Fitza Abtab. And they said, can we predict theoretical voltage using Wien 2K or Wien 2K DFT? If yes, then what's its good range for a cathode? So the short answer is that neither of us have frankly done DFT.
Yeah.
Density functional theory is, to the best of my knowledge, a pretty powerful, useful kind of technique of modeling.
Like electronic structure theory.
Electronic
structures,
working from, I assume, first principles and things of that nature. So, using fundamental things like the Fermi level and the potentials and the electronic structure and the things like that to predict how materials will work, I guess, in reality, something like that, right?
Well, it's usually my understanding, and I know every theoretical or computational chemist I've spoken to, they always have very mixed feelings about DFT. About to say DRT.
I know, that was what I thought it was at first, but yeah.
But there are people feel like there are program packages that you can purchase. It feels like the Wien or Wine 2K package is a DFT package. Some people program their own DFT. They feel like commercial packages oftentimes have inaccuracies in them, or they're not thought out as thoroughly, sort of say. So there's like the hardcore computational chemists who make all their own stuff, and then they run their calculations or simulations, if you will, from that. And then there are people who are, maybe they're organic chemists and inorganic chemists. They synthesize a new molecule, they get some UV vis spectra, they're collecting it, and they need to compare, like, we got these peaks in the UV vis. What electronic structure does that correspond to in the electronic configuration? So they might use DFT to do a calculation for their molecule, to figure out, like, what does this energy transition correspond to? Now that's just with an individual molecule. When you move to things like solid metal electrodes, you can certainly calculate things like band energy structures. So I do think so. The first part of Fizaz's question is, like, can we predict theoretical voltage? And the answer is maybe. We haven't done it before, but I feel like DFT is a program that allows you to determine an energy level, right? So actually, I think that's one thing that's important to note, is that you'll predict, like, the energy of a certain transition. In particular, for a cathode or some kind of an electrode, you'll probably be able to calculate something like a Fermi energy. And then from the Fermi energy, you could extrapolate something like a potential. Of course, potentials are relative quantities, so it's got to be measured with respect to something. So, but then you even made a comment, like, the range of potential for a cathode will depend on the cathode material.
Yeah. And I guess to that point, what I would say is, I sort of made I would make the, I don't know, analogy, or just whatever. Think about reference point, like a lot of people study hydrogen evolution or oxygen reduction reaction, right? And so, for example, the oxygen reduction reaction takes place at 1.23 volts versus NHE. That's the standard potential for the oxygen reduction or oxygen evolution reaction if you're going the other direction, right? But when you're doing reduction, you start at some elevated potential or whatever, and you sweep negatively until you get a reduction current, basically, right? Well, often, as the case may be, depending on how good your cathode is, that's you're attempting to do the oxygen reduction reaction. It's like, well, in theory, you should get the drop off in current, negative ORR current at a little bit less than 1.23 volts or whatever, right? And practically, it's like you sweep, and then, well, at 0.8 it starts to go down. Or I'm just making up a number, but it's like, well, why is that? It should be going down at 1.23, but it's not until 0.8, right? And it's like that is the sort of parlance or the terminology we say is something like, well, it's 400 millivolts of overpotential. This cathode is not that great because it takes 400 more millivolts before you start getting the oxygen reduction reaction. And so that's one way to sort of look at this from the perspective of what's the voltage range that my material is going to do the thing. Well, you can look at the standard E0, you can look at the Nernst equation and shift it based on the concentration of stuff in solution, based on the pH, whatever, and you'll come up with an answer of what the voltage should be. But the reality is that some catalysts are better. Like you try to do oxygen reduction reaction on glassy carbon, and you're going to be like a volt before it does anything, and it's very poor. It's just not a good ORR catalyst. Which is what makes it a great substrate, because it doesn't do a lot of ORR itself. Platinum, much quicker, right? Ruthenium and indium and palladium, somewhere in between. So there's a lot of answers to that. So without having done it, my impression is that something like DFT or just anything like that with real first principles kinds of modeling based on electronic structure and fundamental properties of these materials might be able to elucidate like how good a material is going to be at doing the thing. And then once you know that, you can, figure out what the range should be. So, if the cathode material for like a battery intercalates lithium at, 1 volt versus Li plus, in theory it should. And then your DFT tells you, well, it's actually not going to happen until I go down to 0.7. Well, then you have some knowledge of a voltage range. You should probably start a little bit above the theoretical. You should probably go a little below where it happens. You have a strong enough driving force. Like you can come up with some numbers that'll make some sense, right? If you're going to do a sweep or charge discharge experiment. So things like that would be my assumption as far as getting those values from that. Of course, I'm also just guessing that the DFT is going to give you that kind of detail of like practically how well a material will do the reaction of interest, right? Maybe it doesn't. Maybe that's just only determined experimentally. Like maybe you have to throw the thing in a battery, and in the same way that we do experiments on catalysts for oxygen reduction reaction, and researchers publish all the time about its overpotential was 300 millivolts and it did it this potential at 10 million per centimeter squared. Those are things that people discover through experimentation, for a reason, not necessarily because they can't model it, maybe, right, but also because that's the best way to figure it out. So it might be a little bit of both, right? You might do some DFT, you might require some actual experimentation to figure out the voltage range or whatever that is necessary.
You mentioned the Nernst equation.
I did. I saw you. I saw you get a little happy over there.
Yeah,
I saw you smiling.
It's like you mentioned it first, not me.
I did. I know. I was gonna break. I didn't want to break my. I was on.
You were on. You were explaining.
But I peppered
exactly.
the Nernst equation in, and I just and I knew you weren't listening to anything else. You heard Nernst equation.
I just heard Nernst equation. I'm like, you
brought
it up
equation.
first.
Alex's favorite equation. I did that so you'd be in a good mood.
I am, and
right.
I'm in a great mood.
Yeah,
I'm in a
right.
great mood.
For me, it just takes coffee. For you, it takes the mentioning of the Nernst
just
equation.
mentioning of the Nernst equation.
We're very simple creatures. So now that we're in great moods, we can answer Jesse's question.
Yes.
So Jesse says, I would assume for linear voltage sweep, the range of the voltage applied is important. That is a good assumption. To keep from damaging the cell, what is an applicable range? So that kind of dovetails on what I just talked about, which is, well, you could talk about finding the voltage limit
Yeah.
in CV or in sweep or whatever.
Hmm.
But I don't know if this second question is related to the first. He said, I've been reading on SEI, a solid electrolyte interface or interphase, and supposedly a voltage sweep can disrupt the cell and prevent it from being useful. So this, yeah, so it does seem like your first question is in the context of batteries, in which case you're talking
Yeah.
about the SEI formation. This is something that's a bit,
Because you don't like to do cyclical
yeah,
voltammetry
it's,
or linear sweeps for batteries.
you can, but it's tricky. So let me
Yeah.
try to illustrate it, I guess, a little
Mhm.
bit. For some reason, I tend to finding the right words to say for this philosophy or this phenomenon is tricky, and I don't really quite know why. It's hard. So, I'm not sure. Okay,
Yeah.
so let's say a battery. Batteries typically operate between two voltages, right? We have a voltage, a lower voltage, and an upper voltage. And you can think about a battery, as we typically do, if it's like our phone, right? Try to draw this in a different way, maybe that I haven't before. And it's like we have 20%, 40%, 60%, 80%, and then 100%, right? And so however much of this is filled is how charged this battery is. So this would be like 100% charged. And if I were to get rid of, if I do that, that's 80% charged, that's 60%. You get the idea, right? But basically the point I'm making with the voltages here is that it's actually, and to the best of my knowledge, I guess I usually say this and I assume it's still true. There might be more sophisticated like battery management programming and maybe AI is playing a role. I don't know where we're at now
Mhm.
in an industry, but effectively what we're doing is these states of charge, like this is 0% down here, and this is 100% down here, 100% up here, like charged up. It's basically a voltage reading. So I mean, effectively, in a very small way, you could think of the battery as its charge discharge curve is usually like this. And so we take this middle portion that's relatively linear and we say voltage here is 0%, voltage here is 100%. So it's a voltage reading. Okay, so why is this relevant for your question about a sweep? Well, let me explain, right? So most of the time what we're doing when we're charging or discharging a battery is we're putting current into it or we're taking current out of it. And as we do that at a set rate, it's called the C rate, the voltage of the battery goes up or down. And it's going to go up or down relatively linearly, but we're controlling it not by voltage, but by current, because the current is the thing that's driving the reaction that we're doing. Like whether it's, you're surfing Instagram on your phone or you're driving a car or whatever, it needs current. It needs a certain, so we want to know how much current we're getting out of it. Its voltage is almost secondary. And in cyclic voltammetry and things like that, often the voltage is primary because you're controlling the voltage and you're measuring the current. But in this case, most of the time with a battery, it's flipped. This is why we do batteries galvanostatically, because most of the time we need to know how much current are we getting out of this thing. Like, like for a light that's running on a battery or a phone or anything, right? It needs a certain amount of current, like a huge amount of current or a small amount of current trickle over a long period of time. And so that's the electricity, right? That's the thing that matters the most in most of these cases. And so that's why a battery is sort of fundamentally predicated on current. And then the voltage is the thing that you're measuring. So here's to your point, why is sweeping sometimes a problem with respect to the SEI and whatever? One of the fundamental reasons why that can be a problem is because if you're doing a cyclic voltammogram, what are you doing? Well, you're controlling the voltage and you're measuring the current. And so what you're doing is you're sweeping. Let's just say that you're intelligent and you pick your voltage limits on your CV between the known voltage limits. I mean, anything other than that, and you might be in trouble. You might be over discharging or overcharging. Okay, fine. So you're wise enough to pick the voltage limits. Let's say this is zero current, right? You're wise enough to pick voltage limits between the upper and lower boundaries. Okay, but now let's say you inadvertently pick something like 10 millivolts per second, and this is, 1 volt range. I'm just making this up, right? Well, if V U minus VL is 1 volt, and my scan rate is even something like 10 mil, that seems slow by conventional standards. Well, how long is it going to take to scan from VL to VIU or whatever in between the two? It's like 100 seconds. That's like a minute and a half. So if you think charging your battery from 0% to 100% in a minute and a half sounds reasonable to you, which it shouldn't, then you're going to be in trouble, right? This is why, at the very least, if you're going to do CV, it's got to be very slow. So one of the answers, Jesse, that I have to your question or your point here could be that people say it's a problem. It might be because they're scanning way too fast. Because when you apply a current, the voltage will go up or down at some rate, and you usually make that a moderately slow rate. Like it's dangerous to charge up a battery or discharge it really fast. Like if the battery is fully discharged, like you wouldn't accept it if your phone was discharged in 2 minutes. Your phone should last all day, or at the very least like 6 hours, unless you're obsessively, scrolling
on Instagram,
TikTok, and you never put your phone down. It's probably not going to last so long. Okay, whatever, but you get the idea. It's not going to last a very short amount of time. So consider that's when the voltage goes from VU to VL, or when you're charging it. Yeah, sometimes these fast chargers go for like 40 minutes or an hour, but a lot of us charge your phone at night. You can let it slow charge. It can take a few hours to charge. So imagine doing a CV. It should take at least like an hour to sweep. Well, that's a long CV. So if you're applying your normal logic of CV to a battery CV, you're probably charging your battery too fast. That's why CV isn't always wise. The other reason that's built into this is that as you do your CV, for instance, let's say you go from VU to V, you go scan negatively. You might get a peak depending on how fast you scan, all this kind of stuff, and then you'll get maybe you get a peak. Usually, like in the first scan, you'll get a big negative peak, and something like this indicates the SEI formation. So if you did that really fast, again, without taking some of this into account, you might be forming the SEI in a very bad way. Like it might not form properly. And so it could be unstable. It could lead to, if the SEI collapses, you could have a catastrophic failure of your battery. Things like that are prone to happening. And then the other thing is that look at the current. So if I'm scanning, for example, this direction, well, the current is low here. It's high here. It's back to low. It's high. I'm not charging or discharging my battery at a set rate at all, right? I'm not actually controlling the current in this case. I'm controlling the voltage. So that's a problem in and of itself, because actually, if you consider, like, let's say this is the SEI and this is the, charge discharge peak or a redox peak or whatever. The reality is that you've actually done most of your charging and discharging over this narrow range. And the current was changing. So it's like you're actually charging or discharging your battery at a very unstable rate. Now, sometimes that does happen practically, like if probably an electric car, if you're accelerating, it's discharging really fast. And if you're, cruising on the highway, and it might be even charging or discharging very slowly from trickling, the charge as you drive or something like that. But as a general rule, you want to try to avoid very rapid charge discharge or changes in that rate all the time. And that's what you're doing when you're doing CV, is you're necessarily not having the current be a steady value. It's changing all the time. It's going a lot, and then it's a little, and then it's a lot, and a little. That's what a peak is. The peak, peak is a change in current dynamically. So that isn't to say we don't do CV. We do often still do CV, because a lot of times we're looking for the presence of a peak to make sure that it's doing the charge discharge reaction. Okay, fine. But we don't usually do cycling tests or, most of the study of the battery through voltammetry. We do galvanostatic charge discharge. You want to use it through current. So you wouldn't likely want to do 10,000 cycles of cyclic voltammetry or linear sweep voltammetry on a battery to see how well it holds up or how its stability is. You would do that through galvanostatic, charge discharge. And so, finding that voltage range and sweeping and everything, having it be disruptive with the SEI can happen because if the SEI isn't formed, the first charge discharge that you do on a battery very often, galvanostatically forms the SEI, but it forms it at a very uniform rate. You try to charge it up kind of slowly, with a moderately smallish current for its capacity, and that kind of the SEI sets up, and then it sort of facilitates the charge discharge in the future. So if you mess with that process, you can have some disruptions. You can have some problems, for sure. So the only other comment I guess I would make about as it relates to applicable range is just to be very careful. You talk about this when people ask less in batteries, I guess, but still applicable, I suppose, for anything. But with electroanalytical chemistry, very broadly speaking, you can think about finding the voltage range for a sweep as a trial and error, kind of an iterative process. So it's like you sweep between these two limits and you slowly extend it and you slowly extend it, you slowly extend until you start hitting the edges of, which in the case of batteries is different than something else like aqueous stuff. You start getting hydrogen evolution, oxygen evolution, or whatever. It's kind of an easy indicator. With batteries, it's a little different because you have to, you actually would want to be much more cautious with that kind of investigation, because pushing the voltage limit a little too far could have really catastrophic effects. Not just, oh, well, I've hit oxygen evolution, I can kind of just pull back now. It's like, no, you might have just overcharged your battery or over discharged your battery. And doing that can damage the material fundamentally and prevent it from even being able to be further tested. So you want to, a lot of times I think people, as battery researchers, you want to, even if you don't know, let's say, how much capacity your material has, how well it's going to charge and discharge, you at the very least want to have voltage limits settled before you do any battery tests. Because without that, you could severely overcharge, over discharge. You could have disruptions. You could have issues with the SEI forming and collapsing, and yeah, those are big problems. That's something I studied when I was a postdoc, was thermal runaway. Fortunately for me, I was supposed to make it happen.
Yeah.
So the batteries were supposed to fail
Yeah.
and explode. And so I didn't have to worry about that too much. But most people do want to worry, because you don't want your phone exploding. It's not a good idea.
It's not a good idea.
That's my advice for you. If I have to pick between my phone exploding or not exploding,
probably pick the not exploding.
I'm going to pick
option,
not exploding
option. It sounds like a good option.
It's good advice. Isn't that good advice?
A good choice.
That's what you come to this channel for, is this expert advice.
Yeah.
You choose to have your consumer electronics not explode. if the options are not explode. It reminds me, there's like an SNL skit with Will Ferrell was playing like you wouldn't, that's another sports ball reference, but he played a guy named Harry Carey, and he just does this goofy accent. And it's Jeff Goldblum. He's interviewing Jeff Goldblum is an actor. He's playing a physicist or something, and he's like, hey, if you could choose to be the top scientist in your field or get mad cow disease, what would it be? It's like, I'd pick the top scientist in my field. He's like, oh, good. I thought you'd say mad cow. It's like, what? Why would I say mad cow?
The only reason I know about Harry Carey is because there's a restaurant in Chicago called like the Harry Carey restaurant. It's based on him, and I went there one time. That's the only reason why I kind of vaguely know that name.
Yeah, because you were in Northwestern, so you were from Chicago.
I was from Chicago.
You lived in Chicago for a while. What do you know about Harry Carey? You know anything about him?
Nothing. He
what sport?
He has a restaurant. It's got good burgers. That's
which sport?
Sport. The skim ball.
Skim ball?
Skim ball.
Ball. Sports ball.
Sports ball.
This is fun. You had a 25% chance of getting it right, basically.
Yeah. Is it baseball?
That's correct.
Hey, all right.
Oh, that's so good. I'm proud of you. Yeah, well, he was a Cubs announcer.
Oh, he was a Cubs announcer.
Yeah, he was an announcer for the Cubs for like forever. He had a very iconic voice and a very kind of probably but later in his life, he like
Mhm.
had a very distinct demeanor. Like he had kind of whitish hair, probably when
Yeah.
he was older, and he wore like thick glasses, and Will Ferrell's impression of him is always just really funny because he's just like shaking and just doing this
Yeah.
funny,
Yeah.
like
Mannerisms.
over the top, like
Mannerisms
yeah,
that he has.
mannerism.
Yeah.
And Harry Carey had died, I think,
Oh.
by the time he did these skits. So it was like, it was like funny and meant to honor him, but also, like
Yeah.
at his expense. But it was like
It was tasteful.
he was a beloved guy, like man, like announcer. You know what I mean? So it wasn't like making fun of him, even though
Yeah.
it is. You know what I mean? It's
Yeah,
it's
yeah,
in a
yeah.
in a hopefully in a way that
In a
was
hopefully
trying
it's
to be like
a good
funny
way.
but kind.
Yeah. One other thing, talking about Jesse's question that you mentioned, you were talking about, can you imagine if you were trying to scan, even at a very slow scan rate from from one voltage to another, the amount of current that would have to pass would be super, super high, right? If you wanted to completely charge your battery.
Hmm.
That's also another way to think about fast scan rates in just traditional CV with a 3 electrode system. One
Yeah.
person actually described the amount of charge that needs to pass in a kind of traditional 3 electrode system with like, a diffused redox active molecule. It's a set amount of charge. There's only so many coulombs of charge based on the concentration and based on just molecules that are there, that if you go at faster scan rates, you necessarily have to have higher current because the same amount of charge has to pass in a
Shorter amount of
shorter
time.
period of time. So you basically have to have that. So yeah, I just thought that was an interesting kind of like, the same thinking and logic that applies for just a traditional non-battery type of system also applies for the battery system. Like the battery and non-battery systems both apply the same logic with scan rates.
Yeah, I had a presentation on this some
Mhm.
time ago last year, and I think that was part of my explanation for it. Yeah, it's like
Yeah.
the potential's changing faster, so the concentration gradient
It's
at the
changing
electrode
fast.
surface is changing faster, and so that results in a higher current. It's the same thing as saying more charge is passing over a shorter period of time.
Yeah.
The other is just that um, the scan rate is dq dt
Mhm.
basically,
Yeah.
and you could, I mean, it's kind of a simplistic way. I'm not sure if it's the right approach, but it was one of the explanations for like, why is it,
Yeah.
it's
Why
like
is
you
the
could
current
think of
going higher?
like dt is smaller, dq dt, like the change
Yeah.
in time is now smaller. And so the small is in the denominator. So it makes the
Your
current
may go up.
large. Yeah.
That's absolutely correct.
Yeah. Yeah. It's almost like, why, I guess why that, I don't know, it's always bothered me a little
Mhm.
over the years of explaining, even when I was in grad school or whatever. Cause it's like, I guess especially for like our webinars and
Mhm.
explanations, it's like, I feel like I always want an answer that's satisfying from like fundamentals, and
Oh,
like you
yeah.
can explain it, like and
Like a molecule moves to do this.
exactly, and
Yeah.
we always try to explain things in that way. When it's like, well, why is diffusion? Well, diffusion's random molecules,
Mhm.
whatever. We have a
Yeah.
diffusion layer, and it's like, well, why does the current go down? Because there's less stuff here because they're
Yeah.
moving. Like you can at least envision a real thing happening that's leading to why this is occurring, right? Interfaces, there's a charge transfer resistance, and there's a double layer capacitance, and there's capacitance because there's a diffuse layer here. Like there's things about it, and something about the scan rate current thing always bothers me.
Yeah.
And I never can quite exactly know why, but I think the reason has to do with that. Like, it just is because it is kind of like, that's kind of what we're saying. And it's just, I don't know. It always bothers me because it's like, well, all the charge has to pass and there's less time. So it's just going to be higher. And it's like,
Yeah.
okay, but it's higher, which means that more electrons are flowing. Like, why?
Yeah.
Because it's faster. You know what I mean? It's sort of,
it's a kind of a circular logic.
yeah, it always feels slightly circular logic-y to me. And maybe it just is, and I just have to get over it, which
Yeah.
is very
Well,
possible.
well,
But
no.
it,
If something doesn't like, there are definitely times in science, and I see TT is on, so TT can
yeah,
definitely attest to this, where
yeah,
it's like, someone says something and you're just like, I don't understand that. Like, that doesn't make sense. And then you really have to like ask
meditate
somebody,
on it.
you have to meditate on it, and then sometimes you have to get like another piece of information that's not inherently obvious to help make it
Oh,
clear.
Man,
sort of say.
that's me with the Matschatkey stuff and the semiconductors. Again, I
Yeah.
always feel like I'm bringing this back, but now that I'm like actually finishing
yeah.
my slides for it, and
Mhm.
the only thing that's keeping me from doing it is that you're doing your own webinar series.
You
So
have
I
some
gotta.
travel coming up
That's
too.
true. I
So
have travel,
yes,
yeah,
you
that's
have
true.
some travel.
But
coming
I
up.
can't really do it until you're done. I mean, we got like too many webinars in a
have too
short
many
period of
webinars.
time. I gotta
Yes.
let you breathe on yours. So
Well, yeah.
but no, but that is
See
a
how it
thing that
goes.
like even after our last discussion like a couple weeks ago here in this very room, Alex and I
Yeah.
were like reasoning through how a semiconductor works. It's like
Yeah.
something
yeah.
so fundamental, and you think that like we're at this stage in our career, like shouldn't we either know this or like who cares? Either one of those could have been enough,
Yeah.
And like I refuse to accept that. I refuse to accept who cares,
Mhm.
and I refuse to accept the idea that I could present a webinar on a topic and not really feel like I understand it enough. Because if I'm going to explain it to you all at a webinar, I
Mhm.
need to know what I'm talking about, or at the very least, if there's some small aspect of it, which does happen, that I'm not 100% sure of. I feel like I say this every time we talk about Warburg Open. I'm very open about the fact that there's something about
There's
that.
something weird.
There's something weird about that element that I have a hard time conceptualizing, but I'm honest about that. And I haven't yet found something that satisfies my intellectual curiosity. And so I just am open about, I understand it mathematically, I understand it visually, I understand it fitting wise, but
Yeah.
like fundamentally
Yeah.
it's weird to me in the context that this is just a random example.
Mhm.
But yeah, I think it is kind of funny. It's like I'm also, that's another one of the things I'm waiting for some
Yeah.
like enlightenment moment to happen where I'm like, oh, that's why the current's higher when the scan rate's faster, not just
Yeah.
because it is.
Yeah, not just because it is.
Yeah.
Because something else.
Because this is the way a molecule behaves or something.
Because
It's probably the Nernst equation, right? It's probably the Nernst equation.
Well, for
It's-
kinetics and scan rate, not
It's
the
certainly
Nernst
not
equation,
Lugan
but yes,
capillaries.
it's
I'll
not-
tell you that. Definitely not because of Lugan capillaries.
Oh, God.
Oh my
All right.
gosh.
Well, we have a question from TT.
Yeah, good to see you again.
Yeah, TT says, "Hi, how to solve the Randles-Sevcik equation to calculate the diffusion coefficient and how to calculate it from EIS."
You should show Randles-Sevcik and I'll show EIS.
Yeah, absolutely. So I'll just share my screen first and show you all these useful equations, which is not what I have up. So Randles-Sevcik, which I have here. Here we go. All right, so this is the Randles-Sevcik equation, and I think it's
Yep.
being shared. I'm gonna minimize.
What is happening to my computer?
That's stuff's happening. Okay, I'm also going to hide us for a little bit, just because I'll have a little bit more space to.
PowerPoint presentation going for some reason. I don't know what's going on. Okay,
Oh,
cool.
okay.
You're good. You're good.
I'm good.
Sorry.
Okay.
Yes.
So typically what people use, so let's pretend that you're at room temperature, and we're going to use this simplified Randles-Sevcik equation. So the Randles-Sevcik equation states that the peak current in the cyclic voltammogram is equal to this constant times the number of electrons transferred, so the 3/2 power, times the area of the electrode, the concentration of the species that you're looking at, the scan rate raised to the 1/2, and the diffusion coefficient raised to the 1/2 power. And so oftentimes what happens is you will do a cyclic voltammetry experiment where, let's say, you're doing an oxidation reaction or something, and you have A is going to, or in equilibrium with B plus an electron, right? And so we scan positively, we get this oxidation. Oh, no, actually, we get the oxidation going the other way because.
Why does undo work for you?
Not
for me.
I don't know.
I'm very jealous.
This computer has its own set of problems and
but
stuff.
undo isn't one of them.
You also have a lot of things like.
I'm very jealous.
For those who don't know, from a production standpoint, like Neil's computer is connected to more things. Like
I'm running this live stream.
You are running the live stream. I'm just like a passenger on the live stream. even like my voice going into the mic, it's going through your it's going through your computer.
Right.
Like my computer is almost off.
I'm in charge. Don't you ever forget.
He is in charge, large and in charge.
But I can't undo.
You can't undo.
No matter how much I want to.
So in that case, I win in that case.
That's correct. You do.
That's my small victory.
That's exactly right.
So this value actually, truthfully, here to here. So I'm actually going to erase. I'm going to erase that x, but from here, the current represented by this line. So this this was taken at, say, 50 millivolts per second. 50 millivolt per second. And you have a current that is this distance, this y value here. That current is the peak current, and it's equal to all this stuff. What people commonly do is they'll do a variety of different like scan rates. So they'll keep doing this. No, it's not like that. They'll keep going at a variety of different scan rates, and they'll get higher and higher current. So this may be 200 millivolts per second. This one maybe is 100 millivolts per second. So you'll do this scan rate study, and what will end up happening is you will collect two sets of data from this. You will collect the just skip the review. You will collect IP. So you'll collect the peak current. You'll have the scan rate, but then you'll also take the square root of the scan rate. This is something that you'll do in something like Excel or something. So you'll have a bunch of values here, a bunch of values here, and a bunch of values here. And then what is commonly done is you will take your peak current, you will plot the peak current as a function of the square root of the scan rate. And this, and I've done this this kind of work before, and we do these in some of our workshops. But you will, for not even that well behaved of a redox species, you will get a straight line. Like this equation works extremely well. You will get a straight line, and from this you'll get you'll do a linear regression on this line. So linear regression, and Excel and other programs can do the regression for you. But from this linear regression, you're ultimately going to get something like a y equals mx plus b, where m is the slope, b is the y-intercept. And from this m value, if we go back here, this m value will be equal to all this stuff except for the scan rate. That's crossed off. So once you have a value, you'll have m instead of current. You'll have m is equal to all this stuff. And then you can start to solve for the diffusion coefficient. So ideally, this is a constant, and there's an assumption that you know the number of electrons transferred. Typically, it's 1. It's very rare that you'll get a concerted 2-electron transfer for a redox reaction. So usually this is 1. The area of the electrode, and make sure that you have the right units. Area is typically, it depends. For most planar electrodes that are well polished, you can use the geometric area, but sometimes people will use the electrochemically active surface area. Concentration is something that you should hopefully know. You weighed out how much of your species is there. And hopefully these are considered knowns, and then the diffusion coefficient is your only unknown. So it just becomes a little bit of algebra to then pop out a diffusion coefficient. Take the square root, or square the whole thing, and then you'll be able to get your diffusion coefficient. So that is how you would use the Randles-Sevcik with cyclic voltammetry to calculate a diffusion coefficient.
And then from EIS, let me jump into that. I'll kind of go through this. It's I would say it can be trickier actually. And mainly the reason is that you have to hope that you have Warburg behavior and that it behaves well, and that you can do circuit fitting from that EIS data. So it comes from the Warburg diffusion and the Warburg element. So basically, again, it's predicated on the idea that you will be able to get data that fits something like this circuit. So the Warburg, the W in here, is the thing that you need to be able to get a solid fit for. Whether it's the infinite Warburg or a finite Warburg, you need to be able to get a Warburg coefficient. And so this is the phenomenon of diffusion going to a surface, which is reaction, the species diffuses away, similar to what Alex just showed. I think you had A and B also, so helpful. There you go. Whether it's a reduction or an oxidation, basically you have two species, there's diffusion going on, right? The equation for the impedance is here. Basically what we have is whether this W is defined, sometimes in software it's in the numerator, sometimes it's in the denominator. Sometimes this is inverted, like 1 over W, 1 over sigma. There's different ways that it's represented. But basically this equation, this is from Barden-Faulkner directly, the Warburg coefficient, when you get it from circuit fitting, is equal to all of this stuff. And you can see that there are diffusion coefficients in this expression. So we have RT, those are constants, ideal gas constant in room temperature or whatever temperature you're at.
Mhm.
Again, N, number of electrons transferred, usually 1. Faraday's constant in the surface area here. Again, you have concentrations. Now you have two different concentrations, species A and B, and you have diffusion coefficient. Again, there's a 1 square root, so you'd square it or whatever to get your diffusion coefficient. There is kind of more of a next level thing. I'll just kind of dive into this here. Since we have a little bit of the time to do so, one of the follow-up kind of interesting phenomena here is that this is the expression for the Warburg constant. And so there's a fundamental question about when you're doing impedance. This is why I kind of like the Randles-Sevcik way. It's a little more straightforward. It's like you just do sweeps and you're presumably measuring the diffusion coefficient of the species of interest, which probably is species A, I guess, if it's like A is diffusing and then B is the product. You're probably interested in the reactant, the thing that's reacting. But there's an open question with impedance, at least, that you have a potential at which both species are present. Which is the one that's diffusing? Which is the one that you're measuring its diffusional impedance? It's an open question at the very least, right? So to answer that question, we can actually look at, here we go again, the Nernst equation.
Nernst equation.
See, Alex is,
I didn't even bring it up.
You didn't bring it up. I brought it up
You
twice.
brought it up
Twice today. This is your kind of week. You didn't have to talk about the Nernst equation. I get to. So basically the Nernst equation is giving us a relationship between potential and concentration. And that's in this Q term, right? So in this case, I'm showing it as a reduction. Doesn't matter, oxidation reduction. A plus an electron goes to B. Usually, again, N is typically 1. This Q is activities, but we often just assume concentrations. And so technically the reaction quotient in the Nernst equation is CB over CA. Okay, so what we have here is that if I'm at, for example, right at the E0, if E is equal to E0, this second term is 0. Because look, just by the Nernst equation, RT over NF ln Q has to be 0 if E is equal to E0, right? So what that means is that CA is equal to CB because the natural log of 1 is 0. So that makes this whole term go away. Okay. So what does that mean for this expression? So the main takeaway here and why the impedance approach for diffusion coefficients is kind of tough. It's murky. And it requires you to know what potential you've done the impedance at in relation to the standard reaction potential. So that's what kind of makes it a little bit ambiguous. The reality here is that when CA is equal to CB, you have these both into the denominator, but they're equal. So you can't really cancel one of these terms necessarily if both of these have some appreciable concentration, right? If the product B is being produced and has enough appreciable concentration, at the electrode surface or whatever, then you can't necessarily neglect it. Okay. And so what we kind of have, and this is probably the reality, to be honest, for the Randles-Sevcik equation and that approach, is that the diffusion coefficient you're measuring is some like composite, if you will, of A and B. Now, part of the silver lining to that is that, let's just say for a simple 1 electron redox process, A and B are probably pretty similar in general. structurally. They just differ by 1 electron, right? So it's like if this is ferri and ferrocyanide, I mean, it's probably technically statistically true, but like how different can the diffusion coefficients be for ferricyanide versus ferrocyanide? Like diffusion is just random motion, how fast and how well that happens, how much area it moves over some particular amount of time. Like how different can those really be? I guess. But nevertheless, you might be interested in just one of them, perhaps, I suppose. Or it's possible there's some really big structural differences between A and B for whatever reason, and they do have different diffusion. So when you are at a potential like this, and when you do the Randles-Sevcik equation, you're probably getting, it's technically some aggregate of both species, but we just sort of assume it's one of them, something like that. With impedance, you could I guess look at it 2 ways. One is that it's a bit murky which species you're measuring. Another is to look at it that you can actually manipulate the potential, which manipulates the concentrations and allows you to sort of pinpoint one diffusion coefficient over the other. Now they might be basically the same, but if you consider the case where E is less than E0, that means I'm pushing the reaction towards the reduction. Okay, it means that this quotient is positive because the natural log of a positive number is positive. That means the minus RT over NF term is positive, so that E0 minus a positive number is less. So E is less than E0. So what that means is that CA is less than CB, or CB is greater than CA. This whole term is positive. What does it mean for this expression? When my potential is this way, my concentrations are this way. So if CB is if CB is larger than CA, 1 over the larger one cancels because it's in the denominator. So basically, one way to look at this as an additional manner of thinking is that if I am at the reduction potential, let's say, for my reaction, I'm less than the standard potential, and I want to measure the species A in solution. That's primarily what I'm measuring in theory by picking that potential. And then you can go the other direction, the exact opposite happens, right? If this natural log term is inverted, it's negative, minus a negative number is positive. So CA is bigger. This term cancels. I can measure by shifting the potential in the other direction. I can, in theory, measure the diffusion coefficient of the B species. It's somewhat counterintuitive. I know the reality is we're sort of measuring the species that's in lower concentration because mathematically it works out that way. But it also is, again, it's tricky because it's predicated on the idea that I have data that works well for fitting with Warburg pretty accurately, which isn't always a given. Mm-hmm. It's tough. It's tough to do that. I don't always advocate as heavily, even though I'm kind of the impedance person here. I tend to advocate more for things like Levitch or Katecki-Levitch or Randles-Sevcik for some of those calculations. They feel a little more straightforward to me. They feel a little bit more accurate at times. Impedance is it's tough. It's tough to be real accurate with impedance with calculations like that. But anyway, hopefully that kind of shows you how to calculate diffusion coefficient through a number of different ways.
Yeah. And TT does have a comment or a kind of a follow-up. It says N is for the number of electrons of my active electromaterial that undergo redox, and not those of the electrolyte ? And see, I know the weight of my material in the electrode. I just convert the grams into molarity. So it sounds like you have. Yeah, so let's kind of clarify that. So you may have like a heterogeneous, maybe you have an alloy material, you have some kind of heterogeneous electrode. The number of electrons transferred is based on the electrochemical reaction. In this case, what we were doing was A plus an electron goes to B, or A goes to B plus an electron. Most of these are what we would describe as a homogeneous reaction. But really, even if you have a heterogeneous reaction, and you have, I'm making up something like gold, right? Or platinum. So if you had platinum, for example, and you're forming platinum oxide, right, and you have some kind of oxidation reaction occurring, that may be a 2-electron transfer process. Even though it's a surface-bound thing, you need to look at what is the what is the fundamental electrochemical reaction that's occurring. That is what the N is. It's the number of electrons transferred for that particular reaction. And keep in mind, it may be the case that while you're doing things like cyclic voltammetry or EIS, you're doing it at some, maybe EIS had a particular potential. That potential may induce multiple electron transfer processes. So, as Neil said, for something like HER, for the hydrogen evolution reaction, that is a 2-electron transfer process. That may consist of 2 elementary steps of 2 single electron transfer processes. But in the case of studying, say, your catalyst or your electrolyte or the redox molecule, those 2 single electron transfers would count as an N is equal to 2 if you were, say, using or doing this via EIS or something like that. So that is something to keep in mind. You should base the number of electrons based on the reaction that's going on. And so you can have and just like the case of platinum and oxygen, it's not just like it's like one platinum atom to one oxygen atom is giving you 2 electrons. There may also be cases where maybe you have 3 or 4 active sites on the catalyst or on the electrode, and then that undergoes like maybe a 1 or a 3 electron transfer or whatever to the molecule. Well, that is the fundamental reaction, and the N is the number of electrons transferred in that particular situation. So based on that, and you're trying to figure out things like molarity, taking that into account, you know the weight of your material of the electrode. You can convert it to grams and then grams to moles and then get like molarity. But really, like, it's only the surface. Like the surface, if you have a flat like electrode, it's only the surface of that material. Let's see. TT has another comment. I think this should hopefully provide a little more clarification. It's a battery type supercapacitor. Metal over film, or sorry, metal organic framework is composed of 6 metals. So I thought these metals are involved in the electron transferring, and those from the electrolyte. So yeah, so the yeah, so for a metal organic framework that has 6 metals, yeah, so that's like the unit of the metal organic framework. I think you do need to know what it is. This like how many like there's an A and a B. There's the MOF, and then there's the thing that it's doing the electron transfer to. It may be the MOF, like it might not be actually like, just like we have examples of like ferrocyanide. The electron transfer is to a molecule, and just the oxidation state of that molecule is changing. If you just want the material itself, because I'm assuming the MOF is on like a conductive carbon electrode or something like that. I think, I don't know. One thing I might do is, if you know that there are 6 metals and you think that the electron transfer is happening with the metal, then I feel like there has to be some kind of chemistry thing that you can do to know how many, like, there's 6 metals. Are each of those metals doing an electron transfer? I'm not so sure. I would need to see what the cyclic voltammogram of that looks like, because I feel like you might get something where you may get 6 sequential electron transfers, 1 for each metal, because their redox potentials are different. Or you may get like one very big CV peak that, when you integrate the amount of charge, it's like, oh, this corresponds to like, or the peak splitting is really, really narrow. You may find like, oh, this corresponds to like 6 sequential electron transfers, all very fast. So yeah, figuring out the number of electrons transferred. Some people actually use rotating disk electrodes to figure that out. especially for a system possible like this, for like a heterogeneous catalyst.
And I don't know with a metal organic framework and this kind of a electrode structure, if it's the kind of thing,
Mhm.
a lot of times with the multi electron transfer thing, right? It's like one of them is invariably the slowest, right? And so we sort of end up with like, I don't know what the right approach is, particularly in all cases, but like you could have 4 electron transfer process, but one of those electrons, like they don't actually happen all at once, technically. Like,
Mhm.
right? I mean, it's sort of the theory of, I don't know, electron transfer and kinetics or whatever sort of dictates that there's no such thing as multi-electron transfer. It's one happens at a time. It's just they might happen really, really fast and sequentially. And invariably, one of the steps will be the slowest of them all, sort of almost just process of elimination. Like, if you map out, well, the first electron does this, and this is the intermediate species, and then the second one does it, something like that. So I don't know if you have some situation too where you have like, let's say you have 6 electrons transferred, but like 5 of them are so fast that they're just they're not even measurable. And then the one, so it's like, would you call that 6 electrons transferred or one? You know what I mean? I guess I don't even know the answer to that own question. I'm just presenting that as a thing where
Yeah.
like in a kinetic mindset, you do sometimes have the situation where you have multiple electrons transferred, but only one of them or something like that is the measured kinetically because the rest are so fast, something like that. So I don't know if that's the situation you're running into with your MOF catalyst, basically.
Yeah.
Just mentioning that because I know that stuff like ORR, that's a thing, for example. Like it's one of those things where people do rotating disc electrode, like you said, obviously for
Mhm.
ORR, and it's a somewhat of a fundamental bizarre thing because you're supposed to have one electron irreversible process to be able to do Levitch, right? And it's like ORR is a 4 electron or 2 electron transfer process. It's like fundamentally more than one electron. It's like you shouldn't even really be doing it.
Yeah.
I mean, it's kind of an odd thing. I've seen people argue for this, like, oh, you should never do it. And then the response is that, well, actually, it's 3 of the electrons transferred are really, really fast and 1 is slow. So it kind of behaves like a 1 electron anyway, which lets you use these equations. So it's like some of that, it's a bit of hand waving, you know what I mean? Like it kind of works anyway. So that's all I'm thinking about, just there might be something similar, TT, with your catalyst that has a similar phenomenon of like a lot of electrons transferred, but some of them are just really fast. So it doesn't matter that there's so many, you know what I mean? Like you're not limited per se because some of the kinetics are just really, really fast.
TT also has a following comment. We will get to the question in the middle, but I think we'll finish up with TT just saying, like he says, my CV has only 1 oxidation peak, even at low scan rates, and 1 reduction peak. However, at low scan rate, there are actually 2 reduction peaks. We need to.
I'd expect fast scan rates to show more peaks.
Fast scan rates to show more peaks.
Wouldn't that be right? Or I have that backwards?
Oh, I think
because if it's like a fast reaction, you'd have to scan faster to see it.
Yeah.
Right.
Yeah, if you want to like maybe distinguish a few
like
things,
but like if you have 2 peaks that occur at close, like E zeros, and one of them is really fast, and one of them is like a little slower, the slow one's always going to show up. Like,
well, yeah,
the fast one's probably just going to happen so fast. You like if you're scanning slowly, it's like you won't get time for like buildup of diffusion, like it's,
or if there was a chemical step involved.
Yeah, that too. Yeah, there's a lot of open questions. I just in general, it's like we know, for instance, like scanning, it's just like impedance. It's like you do fast frequency to probe faster stuff. Like in some ways, I would say,
yeah,
I don't know. Maybe there's another thought process behind this.
Yeah, there's a part of me that feels like I need to see the CV.
Yeah,
like it's like, okay, you got oxidation reduction peak, and then there's 2 reduction peaks. Where are they? Like approximately where they are. To a degree, I need to know a little bit more about where, like, I think there maybe is more information. And then, what is a low scan rate? Is it 10 millivolts per second, 5 millivolts per second? And then what happens when you go to faster scan rates? Are those peaks just not even there?
Yeah.
And then you're also correct. It's like, are there just reactions that happening with the electrolyte? So then in that case, you have to we'll change the electrolyte.
Yeah.
Because you can get peaks just associated with the electrode surface. But there still has to be some reaction with the electrolyte itself. Like even platinum oxide formation, it's like, well, yeah, it's got to get oxygen from somewhere to form the platinum oxide or platinum hydride or something like that.
Yeah.
So yeah, I have to think a little bit more about that one, TT.
Yeah.
Hopefully that's helpful. If it's anything, if it's any consolation, it doesn't seem like each metal in your MOF is giving a redox reaction if you're only getting those many peaks,
Yeah.
which is fine. I think that's that's not.
It's probably good. You're not getting a whole lot of disparate stuff.
Yeah.
You know, if it's supposed to act like it's one catalyst kind of.
Yeah.
Yeah. I think we'll leave it there for now.
Yeah, leave it there for now. Maybe we come back to it.
Come
later
back
if
with
we-
any
if we
follow-ups
think-
if you want, TT.
Yeah.
For now, I'll move to Lakshmi has a question. I got Tafel slope around 195 using a catalyst, whereas corresponding final current response is around 240 milliamps over potential of 300. Can you please tell me which mechanism prevails for HER? So first of all, the current 240 milliamps doesn't mean anything in a vacuum, right? This is why people typically report current density. And even then, it's sort of more like it's applicable. You know, I don't know if 300 millivolts is the overpotential. Like, I don't know it well enough because I don't study HER now or OER or anything like that. But people typically, you know, the one I feel like I see most often is 10 milliamps per centimeter squared, and there's some overpotential associated with it. Like, you know, these are things you'll find in the literature, but they're ways of people to correlate to what others are doing in other groups. Because like you might have a 9 square kilometer catalyst and they might be using a micro sized catalyst and there's different surface areas. So how do we compare those two? Well, they got a nanoamp and you got a kiloamp. It's like, well, those aren't, yours looks way better, but you had more surface area and you had a different solution. Like, you know, that's why we have to normalize things to try to be able to correlate. Right. So again, without knowing the numbers well myself, as I'm not a HER researcher, you know, right now, obviously, usually if something like 10 milliamp per centimeter squared at, let's just say 200 or 300 millivolts of overpotential. So just all of that is to say that the numbers that you're saying don't give me a ton of information as far as what I can know. I don't know what 240 milliamps really means, and I don't know exactly what 300 millivolts of overpotential. I mean, 300 millivolts of overpotential seems reasonable, I guess, in general. If you're looking at like a catalyst doing a reaction, like, sure, yeah, that's pretty common. You know, it would be great if it was smaller, but it's okay. Yeah, you get 300 millivolts, you're pretty well driving the reaction relatively irreversibly, and sure. But to your point about the Tafel slope, I assume you're 195 millivolts per decade is what you're doing. I'm gonna have to get on my soapbox about Tafel slopes again.
Figure this is gonna happen.
See,
you did it. You did it, Lakshmi. He's gonna get in his soapbox.
Your Tafel slope probably doesn't mean anything, my friend. As I repeat myself almost every week on this very live stream, Tafel, when you turn your sweep or voltammogram data into a Tafel data, you may very well be making a plot that doesn't mean anything. The Tafel plot is usually voltage on the y-axis and the log of current on the x-axis. And you take the slope of that and you get millivolts per decade. And that's supposed to give you information about the mechanism of the number of electrons transferred or things like that kinetically. That's the key, kinetically. The Tafel equation and the Tafel slope is a direct derivation of the Butler-Volmer equation. The Butler-Volmer equation describes how kinetic current and overpotential are related. I repeat, the Butler-Volmer equation, and by extension, the Tafel equation, and by extension, the Tafel slope, relate kinetic current to overpotential. So if the data from which you made a Tafel plot and then got the Tafel slope was not 100% kinetic data, your Tafel slope means nothing. It just doesn't. It doesn't mean anything. So you might be, you know, discouraged, let's say, that your Tafel slope wasn't 120, because that would, in theory, mean one electron transfer, kinetics, you know, what you would expect for HER. HER is a well, it's a two.
There's two electrons.
It's a 2 electron, so you should get 60
you should be
millivolts
getting
per
60
decade. In
millivolts.
theory, yeah. Corrected myself on the fly there. Yeah, it's a 2 electron process. So it's higher. Does that say something about your kinetics? Maybe, or maybe it says that your Tafel plot is meaningless. So I would encourage you to be very careful and clear about your data and make sure that if you're making a Tafel plot, it means something, because you probably have current and voltage data that is convoluted with capacitance and mass transport and maybe even hydrogen bubbles messing up stuff. And you got a lot of contributing factors such that your I data is not just kinetics. Very probably. So the Tafel slope you got tells you nothing about your mechanism.
Yeah, because you can't have sub 1 electron transfer,
right?
Especially for HER.
Right.
So there's something wrong. That's I think the big giveaway from this whole thing is that, if you had, like, just as Neil said, if you had 120, it's like, okay, that's at least a physically possible number, but significantly above 120, it doesn't make any sense. Yeah.
I mean, you could make some theory that if you say, I'm 100% positive this is 100% kinetic data, which I doubt, but let's just say that that's the case, then maybe there's some weird, maybe in that case it says something about your kinetics being very sluggish or something odd, something strange is happening. But even in the case that you have pure kinetic data, often what happens from a weird looking or number, let's say, of a Tafel slope is that you've simply used the wrong voltage range over which to take the slope. Because on a Tafel plot, the y-axis is the voltage and the x-axis is the log of current. And so the range at which you take your slope could be over here, or you could take it over here, over here, over here. Like, where do you take the slope? Now, if there's a very obvious linear region on your Tafel slope and Tafel plot, and it's real Tafel data, see my previous diatribe, then great, you have a Tafel slope. But it's not. Sometimes it'll be a little curved, or you might go to way too. Your voltage might not, your overpotential might not be big enough. If it's not big enough, it's not irreversible enough, then you shouldn't be using it either. Like, there's a lot of ambiguity and it's tricky. So there's a lot that can be said behind, the application of making a Tafel plot, taking the Tafel slope, and whether it's even valid. So what I caution you very heavily is making really big conclusions about your catalyst, mechanism, electrons transferred, and all that kind of stuff that you're looking to do, drawing a ton of conclusions when fundamentally you shouldn't have even used this Tafel slope in the first place. Back up and make sure that what you're doing is even valid, really. This is it's one of the most common problems that I see in electrochemistry in general, is people making Tafel plots when they should not, from data that's not kinetic. It's such a common practice. That's partly why I'm so passionate about it, because I want to spread the word so people think twice. It doesn't mean you can't make a Tafel plot. It just means you need to make sure, it's one of the reasons why the Kotecky-Levitch rotating electrode method is so valuable, because you deconvolute voltammetry data to extract what is kinetic current. Now, there's obviously errors associated. It can be, it's not perfect. Okay, fine. But it's the theory of it is that you're getting just the kinetic current, IK, basically. And then when you make your Tafel plot, it's like, again, there may be errors. It may not be perfectly accurate, but you can like trust with a higher degree of certainty than I just did a CV and then I made it Tafel. You have a higher degree of certainty that this Tafel plot is really kinetic data. Then I can try to draw conclusions about my slope and mechanism, kinetics, etc. So that's my
soapbox.
It's my soapbox. I'm never getting off this soapbox.
It's not a bad soapbox to get on. I know there are other questions. Some are also related to Tafel, but there's one thing I did want to share related to Tafel plots. There was a paper that I think actually has some really interesting things. One thing people should do, and this is from ACS Energy Letters. It's about Tafel plots and, tools for analyzing electrocatalytic reactions.
Mm.
And one thing that I think is a great thing people should be doing, which I think is what this article is advocating for, is you should plot the Tafel slope as a function of current density. So the idea in this case is that you're actually calculating the Tafel slope at small periods, like 10 millivolt periods, or even like 5 millivolt periods next to each other. And in this case, you can see like, oh, the Tafel slope is pretty consistent over this current density, and it's around 31 millivolts per decade, which corresponds to like 4 electrons or whatever. And similarly with this catalyst, they found that it is only within a specific range of voltage that that they actually had a Tafel slope that mattered. So the measurement of the Tafel slope between different like voltage periods is a good practice, because you might be looking at Lakshmi, you might be looking at like, oh, there's just one slope over this huge, you have 300 millivolts of overpotential, right? Like, but the Tafel slope itself could be changing across that whole range, and you just picked one that gives you a value that's not very useful, or gives you
I
one
need to focus on
195.
a particular potential range over which
Yeah.
the Tafel slopes are not changing.
Yes.
Now, what's the width of potentials? I don't know, right?
Yeah.
Every 5 millivolts, every 10 millivolts,
Yeah.
you're taking the slope. So there's open questions.
They were making some points that like you kind of get the best results every like 10 millivolts or 5 millivolts. If it's 20 or 50, it's a little bit harder in terms of accuracy, because you may only have a 50 millivolt window where,
and it depends how many points like your instrument is giving you. If your potentiostat software, for instance, is measuring points every 5 millivolts, it's hard to get slopes accurately. You have 2 points, right?
Yeah.
So it's not ideal, right? Some of that will be determined maybe by your instrument as well.
Yeah. But anyway, that's just a quick thing I wanted to
point.
at least point out. I thought that was interesting.
Yeah.
Well,
now that I've stepped down off my soapbox, we can get back to being calm.
Yeah.
And Yuvraj has a question. Difference between galvanic and electrolytic cell. Well, very simply, one is spontaneous, one is not energetically. One has a negative Gibbs free energy, one has a positive Gibbs free energy. One has a negative, voltage, and one has a positive voltage by that extension.
Yeah.
Delta G is minus NFE. So I don't know if you want to explain it any more further. Just throwing out the technical thermodynamics answers. But
no, that's right.
I probably should say which is which. I'm just saying one is one.
Yeah, the galvanic cell is one that's thermodynamically favorable, and these are the easiest thing to think about is like a battery. A battery is a galvanic cell. It releases energy spontaneously when you hook it up to a load. An electrolytic cell, by comparison, is like a traditional 3 electrode cell, where I have to use a potentiostat and a power source to drive energy to get the reaction to occur. So that's what an electrolytic cell is, just very simply. Yeah. And I think we're only going into this to this degree of detail because there seems to be quite a few new questions coming in that we want to get to. But that is the answer.
Thermodynamically favorable for galvanic. Thermodynamically not favorable, therefore requiring energy for electrolytic. Yeah. So there you go. Anindita has a question: how to choose non-faradaic region of a CV in a cathodic and anodic scan? I mean, honestly, the simplest answer is find where it's flat. It's sort of a very, very simple answer. Let's just say, as a few kind of examples here. So in example 1, for my cyclic voltammogram, I have this. It's probably not why you're asking the question, but the answer is literally everywhere. So this is this whole range is flat, right? Very good. Okay. That's probably not what's happening in most cases. So let's say you have situation 2, and you might have something that's like you have, multiple charged processes, is like all this kind of stuff is going on or whatever, and it's even tilted a little bit, and it's like, where do I pick? Do I pick here, or do I pick here, whatever? Well, frankly, in a case where you have like a lot of redox happening or a lot of processes happening, you really only have a couple of choices. For instance, if you're trying to find the flat section or whatever, I guess, right? You're either going to have to extend your scan, maybe in this case I found it here, right? Okay, but you'll have to expand your voltage window a little bit to try to find where it might be flat if there's so much like peaks in activity going on. Or if you're just trying to find the flat one to get peak height, for example, then you might just have to sort of make an estimation of like between this point and this point. You know what I mean? Like you'll have to make an estimation to get your peak height between here and here, between the base of where the wave is. Like sometimes that's why people want the flat section. So some of that kind of makes it difficult. And then I don't know, the third one that comes to mind is the platinum CV, which is a very famous one, right? And it looks something like this, the platinum and acid CV. We have oxygen reduction, hydrogen peaks. And so this one has a lot going on as well. And this is the platinum, like platinum CV basically. And this is the region, like there's only one small narrow region where it's just basically double layer capacitance. And it's this region right here. This is platinum oxygen here. This is oxygen reduction. This whole region here is platinum, hydrogen, adsorption, desorption. So there's like a whole bunch of stuff going on, but there happens to be this one narrow range. It's at like, I don't know where the heck it is, like 0.3, 0.4, 0.5, something like that in the middle potentials or whatever, where it's basically there's a flat region and you can get that. So sometimes you just got to know platinum is one of those where it's like, it's well-defined, it's in the middle. Sometimes you'll have to expand the window. But yeah, I mean, generally speaking, you're finding where it's flat as a general answer, right? So,
all right, going on to the next question. Can you help me with pronounce it?
Vignesharaj.
Vignesharaj. Sorry, I'm not very good at these. So Vignesharaj from LinkedIn is asking, I've calculated faradaic efficiency for my organic molecule electrooxidation by using chronoamperometry. By taking solution to HPLC to get concentration over electrolysis for 1 hour, and putting all the parameters, after calculating, I got a percentage in 10,000% to 20,000%. So can you explain why it is? In addition, I guess he says, in addition to that question, I feel like there's some problem in Q, which is charge while calculating faradaic efficiency. So yeah, this definitely seems odd to get 10,000 to 20,000% either faradaic efficiency. Just to kind of go over briefly, like what, because I'm sure once we do something like this kind of out in full, you'll either realize it's let me hide the question for the minute. You'll either realize like, oh, you did something right, you did something wrong. But let's say, so you did an electrooxidation reaction. Let's say this is your chronoamperogram, and so this is 1 hour. All right. So you may have done, and then if it's chronoamperometry, you're holding it at a constant potential, and then your current typically kind of goes like this. And ideally, you're like stirring the reaction as well. That's usually what happens, and then you maybe stop it. That's what people tend to do in a chronoamperometry experiment. And then they will use, and I'm going to highlight this kind of blue because it's easy to see. They will take the area under the curve, right? So current over, if you take the integral, the area is equal to the amount of charge, and that is going to be in coulombs. Q and coulombs. I never spell this right. I always
COU.
COU. I always there's like a U in there, and I never remember if it's on this side or that
It's
side.
like coulombs.
Coulombs.
Yeah.
Coulombs.
Coulombs. Yeah.
Coulombs. It's in coulombs of charge. Now, here is a thing that I have seen, and I don't know if it's a big deal. Where is 0? And like, how is this area calculated? Because if, for example, if 0 is here, none of this matters, right? Like, how you calculate the area doesn't matter if this is 0. You must look at where is your 0 in this, in what's happening. Ideally, you don't have anything that's below 0. But let's say, so let's take that out. So let's say you have this. So that's like the main thing. So you have some number of coulombs of charge, and then you would take Faraday's constant, coulombs per mole. So you would divide this by Faraday's constant, and this will give you the moles of what was created. Okay. Now this assumes, this is just a 1 hour electrolysis, but if you take a sample or an aliquot of your HPLC, then that's not all of the molecules, right, that you're sampling, right? So you do need to think a little bit about how many molecules are you actually sampling, because I'm assuming with HPLC you're getting a concentration and you're not getting moles. Because unless this electrolysis is complete, right, because 1 hour might not be enough time. You might need to wait for this thing to really like dip down to really be 0, right? Only when you're getting like a really low amount of current, when the electrolysis is fully completed, then you can look at like, okay, this is the total, like, how much of the molecule you've added, the grams of it, its molecular weight, you've electrooxidized it into a species. And then, oh, here's the other thing you need to keep in mind. How many electrons were transferred? What is N? Granted, N will not account for a 10,000 to 20,000% change, but Faraday's constant's pretty big, right? Make sure that you're, and then the order of magnitude, do you have millicoulombs, microcoulombs, coulombs? I mean, that's another question. So I feel like this, like 10,000 or 20,000% is really just a math error. And also knowing like, okay, you've done this for 1 hour, you have an amount of moles, but you don't have a concentration, and you need to make sure that you're comparing like apples to apples, the concentration of the species versus like, all right, well, how many moles completely of a complete electrolysis have I converted?
What about if there's any background current associated not with that process? You could be overestimating Q.
Yeah, if there's another
too.
process occurring,
Like
ideally,
even just the
hopefully
charge. I mean, in theory, the charging is sort of in a chronoamperometry. It's like a long period of time.
Yeah,
but if there's some other, like, that's another thing that's built into everything Alex is showing there. That blue highlighted area is making the assumption that the current you're measuring is coming only from that
reaction.
That reaction.
Yeah.
But what if that's not the case? I don't know.
If there's a background reaction.
There's some other reaction happening. Technically, some of it in the very beginning is related to the charging of the double layer or something. So you might have a little. I mean, it's probably not a ton in that case, but nevertheless, make sure that the charge you're determining from your chronoamperometry is for the reaction of interest and not convoluted with something else, because you could be overestimating it, maybe.
Yeah.
So there's that too.
Let's
see. Anandita has another point. I think I can possibly illustrate this. I'm getting higher overpotential in cathodic scan, lower overpotential in anodic scan for HER1. What might be the reason? Let me try to illustrate what I think might be happening. And Anandita, if you're still here and if this is what you're seeing, this is my guess for what you're seeing. And you're like, let's say you're doing a CV and you're sweeping negatively and then positively. So if this is 0, HER happens negative of that, right? So this is current. So your overpotential is basically how much negative we are from zero, right? Where the HER start happening. So my guess is that you're having something like this, where you scan negatively, and then it starts to go down as the HER happening, and then you scan back, and maybe it does something like this. Maybe at some point it'll, like, I don't know, cross, there's that crossover kind of phenomenon. And so, like, the overpotential on the way down, negatively, it would be like, you pick a point, like maybe it's here or something, right? But the overpotential where it crosses on the way back seems to be smaller, like where it crosses zero, like if that's your metric, right? It's like, oh, well, my overpotential for the anodic one was smaller. It's like, it's only this distance instead of this whole distance. So that's my guess at what might be happening. And I think the answer is really more to do with, and I might have even drawn this more, it might have been like, like almost like that or something. I don't know, whatever the curve would look like on the way back, but it does that weird cross thing, where what it doesn't do is, let's say it goes down and then does that, which would be like what you'd expect maybe. And so, like, or just trace on itself perfectly. Like maybe it doesn't trace perfect. So like ideally your overpotential would be the same, whatever. What I think, if that's the case, and this is something that can happen from time to time, this is a time phenomenon. So that's your voltammogram, for instance. Okay, so this is voltage or potential and current, right? And so I'm just going to draw it one more time. But essentially, it's like this, and then you change direction, and it's like, let's just say it does that or something, and then eventually, whatever. Okay, let's extract the current versus time and the potential versus time plots, because the voltammogram is actually consistent of right, two plots, voltage versus time and current versus time. And I think this might, hopefully, if this is what you're seeing, this would explain it. So the voltage versus time is very simple, right? I'm scanning negatively and then I'm scanning positively. So that's probably what your voltage versus time looks for, whatever these numbers are, right? I'm scanning this way and then back. So it's a very simple thing. Now the current with time is that I get no current, or zero or close to zero or something like that. And then eventually the current drops. Okay. Now remember, this is all with time. And so as my voltage goes, let's just say negative of zero, as soon as it gets there, I start having hydrogen evolution happening. Okay. Now at this point here, I don't want to hit undo. I almost did it. I was about to probably crash. Would have been scary. At this vertex where I change the potential, your expectation is that the current will start going the other direction, but that's not necessarily what's going to happen, because the reality is that even though I've now changed direction and my voltage is like decreasing, I'm still at a negative potential, right here, right after the turnaround or the transition, right? I'm still at a negative potential. So the current might not necessarily start to go back right away. It might actually take a little bit of time to go back or whatever. So it's like, if I line these up, and I'll try to show this a little bit, it's like my vertex corresponds to, and I should have drawn this a little better here. Like, it might correspond to not exactly the bottom of where the current is. And so it's like, now my current. So when I plot I versus V, this is what it ends up looking like. And it's like, that comes into play at this point here, where the voltage turns around, but the current doesn't immediately start going down. It's still going up or maintaining its value a little bit or something like that. It depends on how fast you're scanning and the speed or whatever. But the reality is, because the current is still doing HER for some time, because there's still, like, I'm headed positively. I'm decreasing my overpotential. I'm trying to escape the HER region, but I'm still there. Even though I'm scanning negatively, I still am at the HER potential. So my current might still be going, right?
Oh yeah. I was just gonna say.
Was there a comment?
She made a comment. She said, "I'm taking an LSV plot, so it's just a single sweep.
Okay.
She's not doing CV, so the anodic and cathodic scans are single scan
Okay.
LSVs.
So some of this is still somewhat. So like when I'm starting down here, right, and I'm going this direction, or I'm starting here and I'm going this direction. And why are they different? Well, it could be a similar kind of a thing. When I'm starting here, I'm like starting right away. As soon as I turn on the potentiostat to start my LSV, I'm beginning it at a very heavy overpotential where HER is happening. So so you might even have something like that happening where it's like, I immediately start decreasing my overpotential and scanning back, but the current might still be kind of hanging for a bit. And then, so then it artificially gives me a better overpotential because it's the same sort of phenomenon, even if I'm not changing directions. I'm starting where I'm already generating current. So in the immediate turnaround of moving back, I might have a somewhat of a delay almost in the current decreasing because it's happening quite like aggressively. Something like that. Whether you're doing them at the same time or like in this sequential way that you've described, you can still have a little bit of that. You can call it hysteresis, the difference or whatever. People deal with this in different ways. For instance, when it comes to HER or ORR or whatever, I think, I've seen it where like people testing a catalyst for like ORR, there'll be a small hysteresis when you're starting here, starting positive and going down, or starting negative and going back up. Sometimes you'll split the difference if you're trying to say, well, what's the overpotential? Sometimes you just take the best one and you sort of know, like if I start negative, this happens with ORR also. It's like if I scan from negative to positive, my overpotential is a little better. So you'll take that and report that. It's not lying, right? You're just using something to your advantage. It's like I mean it. I don't even necessarily trying to be snarky about it or whatever, but it's like if I scan one way and it's a little bit better, you can use that to your advantage to illustrate, slightly better activity for your catalyst or something. I don't know, something like that. But that might explain it. Maybe there's something else going on, and there could be some other mechanistic kind of thing that I'm not positive. It might depend on your catalyst. It might depend on some other things. But that's just my stab at what might be happening. Anyway, as it's sort of the time element playing a role into it. It might depend on, maybe if you scan at different rates, like maybe if you scan like faster, they would be closer together. Maybe it's the exact opposite. I could be wrong. I don't know. It could have some effect on scan rate, depending on whether you see that kind of hysteresis and difference. I'm not sure. But I guess the last thing I'd say is probably the best, maybe most accurate way, rather than taking the better one or splitting the difference or something, is to get a curve that is just a series of chronoamperometry. So instead of sweeping from positive to negative at, let's say, 10 millisecond or something, or scanning negative to positive, and that's a little better or whatever, is set up a series of experiments where you hold the potential. It doesn't matter where you start at this point. You're going to hold the potential for like 1 minute every 5 millivolts or every 10 millivolts, however long you can stand doing this. It's going to take a while, right? But like over a 400 or 500 millivolt range of your HER or whatever, hold the potential for like maybe 60 seconds is too long, 30 seconds or something. Because then you're getting you're letting the process decay. You're getting a steady state current at every potential. And then you could put those all together and that will make your curve. So that would be a way to get like a polarization curve or I don't know, something like background corrected curve or something like that. That's another way to do that.
All right. There's some more questions. We'll try to get to as many as we can. Alok has a question, just going in order. What could be the possible setting in parameters while ESI recording?
I assume you mean EIS.
EIS, but then I guess the question is, what are possible setting in parameters? Is that while recording or in order to record or generate?
Do you mean like what experimental parameters should you pick for impedance? Is that the question? Like what the how many points per decade, like what frequency range?
Yeah, I mean, I guess
is that the question?
we need some more clarification.
Yeah.
I think about this question, to know what you're
And
referring
do you
to.
mean like, sort of more generalized, again, like what frequencies to pick, what
Yeah.
amplitude to pick? Or do you mean specifically for whichever software you're working
Mhm.
with, what parameters in the software to pick? Or do you not mean impedance at all? And
Yeah,
I'm
or
assuming that was a
there's something else
typo.
called ESI that we don't know
I'm
about.
not sure. So yeah, look, I think you might need to clarify for us if you can. We will.
Mhm.
You mean impedance? Yeah. So do you
Okay.
mean kind of what we were saying? Like, do you mean
Like, what are the
what
parameters
parameters
for?
should you pick? I mean, I can answer that while I wait for you to clarify if that's kind of what you mean. But if what you're asking is what are the parameters you should pick, as a very general rule, most people are studying impedance on. If you're studying impedance on like an aqueous 3-electrode system, HER, OER, ORR, like 3-electrode, something of that nature, most probably you should be doing potentiostatic impedance. Most probably you're going to have somewhere between, let's just say, 5 and 20 millivolts amplitude. You're going to want to have a smallish amplitude to start, and then you can increase it if you need to if your data looks noisy. Sometimes increasing the amplitude helps clarify that noise. So somewhere between 5 and 20. I usually start with 10 to 15 millivolts of amplitude is usually where my go-to. Most commonly, you're going to start at 1 megahertz to 100 kilohertz as the upper range. A lot of software and potentiostats can go up to about a megahertz, but there's usually not a lot of information in a lot of systems above like 100 kilohertz. But you're not going to hurt anything by doing a megahertz. So you could start at a megahertz if you want. And then the highest frequency decade's probably irrelevant, but that's okay. You can sort of ignore those data later. And then I usually will have my lower limit be about 0.1 hertz. So 100 millihertz is usually the lowest limit that I can tolerate. It takes a long time if you go lower than that. And anywhere from 6 to 10 points per decade is usually good. So that's a list of settings that's going to probably apply for most things. If it's a battery, you're going to be doing a little bit different. It can be galvanostatically. But that's just some ideas for frequency ranges and amplitudes and things of that nature that you might be looking at in the software. Hopefully that's applicable to what you're doing, or at least, possibly applicable, I guess.
Yeah. Okay,
let's keep, as usual, we get 1,000 questions near the end.
Yeah.
But that's how it goes. So.
Yeah. Alton's asking, we are doing an EIS experiment and we are expecting a Randles-Sevcik response. However, we just get sharp linear lines with 70 to 80 degrees. What could be the reason for this? So usually you get this kind of response. It sounds like it's more capacitive based on it. The closer to 90 degrees in terms of like an angle, the more capacitive the system is. Also, this is also assuming that this is orthonormal in terms of plotting in the Nyquist plot. So if you're not, so double check, make sure that you are orthonormal. If you're not orthonormal, and what that means is that the resistance on the X and Y axis are the same scale. So like, 50 here is 50 here, as opposed to like 20 is here and 100 is here, because that will also skew how, the degree of the line. But typically it means that you have something very capacitive, generally speaking. But it's also possible, what I've seen or heard people do or say is, if you have if you're expecting a Randles-Sevcik response with like a semicircle and then a diffusional tail, you might just be getting the diffusional tail, but you're not plotting correctly. So it's not at a 45 degree angle. Maybe it's at a 70 or 80 degree angle. And so the question then I ask is, at what potential are you doing EIS at? Are you doing EIS around a potential, right? This is like your baseline, and then you do EIS around it. Is that potential around the redox potential of the molecule that you're trying to study? That is what you would model, what you would model for a Randles circuit. So those are kind of the questions, but based on what you've described, 70 to 80 degrees, it sounds like you have something that's more capacitive. There's like maybe a blocking element or something that's happening. But I need to know. We'd have to know a little bit more about your cell or
Yeah.
your system
I
to
think
really tell you
I think
more.
you're almost for sure correct. It sounds like someone is probably just assuming to do impedance at the open circuit, because why would you ever change that?
Another soapbox.
I can't help myself.
This is great. It's like you mentioned the Nernst equation,
And
and you
I'm
get
triggered.
multiple soapboxes.
I'm miserable and you're happy. It's a good day. Yeah. No. Yeah. If you're trying to study whatever reaction you're trying to study, and you have not applied a baseline EIS baseline potential at which you're doing EIS that is anywhere near or has an overpotential for that particular reaction, then you're not studying that reaction. You're going to get a Randles response when you have a charge transfer process, occurring, because that's the resistor part of the Randles response that gives you the semicircle. So pick an appropriate applied potential, and you'll probably start to see a Randles response. Probably.
Yeah.
That's most probably what is happening.
Most probably.
Yeah. All right. HR has a question about Nova software, so I might not be able to really help here. I'm using Nova software for impedance analysis. Is there any exact method to fit the equivalent circuit with minimum chi-squared value and correct circuit diagram without trial and error? Not really, in some general sense, whether it's Nova or anything else. There's always trial and error required. Now, the lack of trial and error comes from the software minimizing chi-squared. Like, that's what the software is good for. You don't have to usually, do trial and error all the time with a circuit. It minimizes it if the fit is good. Now, the fit's not always good. So, I can speak more clearly for my company's software, obviously, for Aftermath circuit fitting. We actually do have quite a bit of tools with trial and error that allow you to do both, which is that you can rely on the software's algorithm to get you a good fit. And also you can adjust the method from simplex to Levenberg-Marquardt. You can change the weighting from parametric to unity on the fly. You can adjust the parameters with slider bars to see how they change pretty actively. And those are things that our software in particular allows you to do pretty nicely. I can kind of show you some of that just as I'm talking it through. I should probably show it. Showing is better, as they say.
Yeah, I was also going to, I'm going to put in the comments, we have a link to a new video that we came up with, which is on EIS circuit fitting, just a way of just like what you're going through now. You have a whole video that goes over EIS circuit fitting. So if you wanted to, you could watch the video, see if this is a form of circuit fitting that you would like to try for your EIS data. And then you could, in fact, purchase a fairly inexpensive circuit fitting license. Just do it for a month, and then you'll be able to fit your data much more easily.
Yeah.
So this is something you can try.
So to that point here, this is an example. I have two like RQ units, or RCs. And it's like I can see this fit here. This is like parametric. I might have gotten this. Sometimes the software you're using only lets you do parametric weighting or only one at a time. I can change to unity. This one happens to get better. I can move the parameters actively left and right and see how it changes the Bode and the Nyquist plot. So there's some trial and error, but there's also like very quick visual, yes, no, this looks better, this looks worse. Then I can do a final calculation, snap things into place. There's a lot of really powerful tools with this circuit fitting platform here. The only other part of the trial and error that is, no matter how you slice it, requires human intelligence is the selection of the circuit itself. So if you have data that's ambiguous, you don't know if it's 2 or 3 charge transfer processes, or there's a Warburg tail, or it's diffusion, or it's capacitance, or whatever, that may require trial and error, or just your own intelligence and knowledge of your system to be able to know which circuit you should be fitting. And so some of that is really unavoidable. Yeah. until AI takes over and tells us which circuit we should fit,
Yeah.
which is probably already a thing, if I'm being honest. But I hope it's
Yeah. I've thought
Makes
a
me
little
sad.
bit about I think there's some people who are very resistant to like either cyclic voltammetry simulation or EIS circuit fitting, where could you train a model? Because it's the whole like we know some people have said like, hey, I've used Kramer's Kronig. What's the and I get a good result. What's the circuit that used? I'm like, well, yeah, EIS can find, circuit fitting can create, the perfect fit, but does it mean anything physically in reality? And it's like, no, you need to base, the physics of the system, the actual like, thin film layers, sort of say, and interfaces to the equivalent circuit model. You can't just like make up an additional one just so because the fit is better, unless you can back it up with some other kind of scientific, microscopy or spectroscopy, just some other bit of information to help you confirm, like, yeah, I have more than one layer, so I should fit it to more than one circuit element or more than one Randles or Voigt element. So, but yeah, that's HR. I hope that, well, you mostly answered the question, so, but hopefully that was helpful. We have about 5 more minutes. We won't be able to get to everybody's question, but I think we can.
I think we might be able to, well, maybe not. Well, we'll see.
Maybe.
Yeah, on in detail, we can try to answer some of these relatively quickly. For instance, so she says, I'm working on 4 catalysts, let's say 1, 2, 3, 4. The overpotential order is 1 is greater than 2 is greater than 3, greater than 4. And the ECSA order it's essentially backwards. So 1 greater than 2. It looks the same, but the reality is that the lowest overpotential is the best in that metric. And the ECSA, you in general say is the opposite. So in terms of HR activity, which catalyst is best? So this isn't an answerable question. If nothing else, for the simple reason that best is subjective by the metric that matters most, but by whichever metric matters most. So if you are going to say the material with the highest electrochemically active surface area, first of all, the ECSA is also specific. Like a high ECSA could be because you just have a really big catalyst. So if you have the same geometric area, but they have different ECSAs, then that's fine. That's good. Like they all have the same, 5 millimeter disc diameter, but they have different ECSAs. Okay, well then it's comparable, right? Then one having a higher ECSA may mean something. But if it's like, well, this has a higher ECSA, yeah, because it's 4 times the size. Like I have a massive disc of this one and a small pellet of this one.
Yeah.
Well, it has a higher surface area, it has a higher geometric surface area, and a higher ECSA. That doesn't mean anything. It's like almost like specific area, like which is like it's analysis called BET, Brunauer, Emmett, Teller. It's how you get specific surface area. So like how many square centimeters or square meters per gram. So like mass specific surface area is helpful, Now in the case of the ECSA, just is across materials of different geometric sizes. But let's just say they are the same size. This isn't even necessarily an answerable thing, because in some cases, or in some, let's just say, research studies, you're going to very clearly make the case that what I'm after is the best possible overpotential. That's like my goal, is to reduce the overpotential. And so in this case, number 4 is the best, has the lowest overpotential. But in some cases, you're saying I'm trying to make the smallest size nanoparticles I can with the greatest surface area. So I want the highest ECSA I could possibly get. So 1 is the best, right? There isn't really an answer there. It's kind of, what is your goal? If your goal is something in between those two, well, then 2 or 3 is probably the best one. Like, right? You know what I mean? It's like, this is why it's not answerable, because best is really a subjective kind of a thing. So it depends what you're trying to maximize or optimize, let's just say. If you're trying to be fair across all of the different metrics, it's probably something in the middle. That's the best way I'd think about it.
Yeah, I think actual catalysts are are not just evaluated on the overpotential and the ECSA. You know, there's the cost, there's the weight, there's practicality,
longevity, how
longevity,
well, it's got a great
stability.
overpotential, but after 3 cycles, its overpotential is terrible.
Yeah.
Like that.
This is kind of a reason why we have so many catalysts and that we have so many batteries. It's like there's so many batteries based on like lithium, but but like we have so many of them because there's no one battery type that like it fits every single application. It's like no, we need different batteries, different battery chemistries based on the same, like maybe, you know, lithium or something. But we need different batteries of different sizes, different chemistries, because we have so many different applications. And
what works in a electric vehicle isn't necessarily what you need in a smoke detector.
Yeah, exactly.
Right?
Exactly. It's a great example.
Okay.
Yeah. Oh, and Jesse asked about the
I put the link for the voltammetry series for the webinars. So
yes,
check that out next week. Alex is starting the voltammetry series. Very exciting.
Yeah, and it should be on the YouTube page. I've made all of them kind of like unlisted. So if you are on the Pine Research YouTube page, I think if you go to live, you will see upcoming videos, which will be live streams. So I made just this thing for for people who are looking next week. You know, I'll be doing this voltammetry series thing. So there'll be one each week in September on the Thursday. So the 4th, the 11th, the 18th, and the 25th. Some 20 something. The last one, I forgot the date.
4/11/1825.
25. That's it. So, so yeah, just you know, hopefully you'll decide to join me for that if you want to learn about voltammetry, and yeah, go to the Pine Research website, which Neil just put into the YouTube chat to register. And really, the truth is, registration it just gives you an email reminder. It's just going to give you an email reminder and a link. But you can just show up. Like if you just remember the date and the time and you come to Pine Research, either on LinkedIn, YouTube, or X, I'll be streaming to all of those platforms. So any one of those is fine.
So yeah, I think we'll probably call it here. Sorry, TT, I said you have a question with impedance, and then there was a bit about specific capacitance. To be honest, I don't know exactly how to answer that. I know more about capacity than capacitance.
Yeah.
Anyway, but we're at the time here, so we're gonna
wrap it up
here. But thank you everybody for another episode this week. We have one more week, and then very possibly we'll be on a break. It's possible from while I'm traveling, I might be able to join. TBD.
Yeah,
I'm not sure yet.
It's okay.
I'm not exactly sure what, frankly, country I will be in at that moment in time. So if I'm in a country and it is possible to be in a stable location, I could do it, but it remains to be seen. But if not, we will have a couple weeks off maybe. So until then, we'll see you next week.
All right.
And thank you everybody. Take care.
Bye.
Bye-bye.